Out tonight, and you can see the title that I'm working with here. So I thought I'd just start by just giving you a little brief background on why I'm talking about this topic, being an astronomer rather than a climate scientist, since you usually might not think of an astronomer talking about global warming. It is actually an astronomical topic, and I will explain that to you fairly shortly. And so I have been actually teaching about it as part of my astronomy teaching for more than 30 years. But the way this particular talk came about was because of the relativity talk that Kim mentioned she saw me do. That was in 2015, and that was because that was the 100th anniversary of Einstein's publication of general relativity. And for that, they asked, the physics community asked for people to do public outreach events, and since I'd written a book about relativity, I said, well, I'll do that. So I sent out an email to people and said, if you want me to come talk about relativity, I will. And I ended up in 25 cities that year speaking about relativity. And I had so much fun doing it that when 2015 came to an end and that no more 100th anniversary, I was like, well, what do I do now? And I thought I should do some other topic. And I thought about it and I decided global warming would be the right topic to do. Number one, because it's such an important topic, but number two, because it has so much in common with relativity. Namely, that it's something that among the public, everyone's heard about, but very few people understand at all. And so I thought maybe, just like I tried to make relativity understandable, I could try to make this topic understandable. And with that in mind, I'm sure you probably all heard that there was huge news today in that we got our third detection of gravitational waves from two merging black holes. So it goes right along with my relativity talk. So that's quite an amazing thing to hear. This was a really cool one. So anyway, what my goal is today is to tell you about the science, the consequences, and the solution. So I started doing this tour, and I didn't have a book yet, but then I quickly found out that I couldn't answer everybody's questions in 1 hour, so I wrote a little book to answer all the questions. And then I found out some people don't want to spend money on a global warming book, so I posted it for free at globalwarmingprimer.com. So you can either buy it or you can read it for free online, whatever you want. And any questions that I don't get you to today, I will almost guarantee you they're answered in here in question and answer format, because I've heard all the questions by now. One of the things it has in common with relativity, when I talk about people not quite understanding, it actually has in common with a lot of other science topics, which is that you get people not really having a clear understanding of what's going on. And I think it's because of a flaw in the way we teach science in general. And that is, we tend to teach kids at any age, whether it's, high school, college, grown-ups, we tend to teach people all these details about science. But we often forget to tell them the basics, the big picture, where these ideas all come from. And this is one of those cases. It's kind of the literal missing the forest for the trees, where you listen to the debate that goes on in the media, and you hear people arguing about all these details, but you never hear anybody say, what is the basic science behind this? And that turns out to be relatively easy to understand, even though no one talks about it. And so my goal, it will work better if I plug in the... So my goal, and I shouldn't talk about this, my goal is to help you understand the basic science, tell you a little bit about what the debate that you hear is about, and talk about how we can solve this problem. And I'll move pretty quick so that we have plenty of time for discussion. So I told you it's an astronomical topic. And we start out by thinking about this topic through astronomy. So what you have here on the screen is Earth and Venus, and they're shown to scale. And what you see immediately is that they're the same size. So Earth and Venus are two planets that are the same size. They have the same overall bulk composition. So in other words, they're for the most part identical twin planets. But there's one really major difference between them, which is that on the surface of Earth, the temperature is very pleasant, 15 Celsius or 59 Fahrenheit, whereas on Venus, the temperature is hot enough to melt lead. So you might, if you're thinking about this from a scientific standpoint, the kind of question that you should ask if you think scientifically is, why would two planets that are overall so similar be so different in just this one way? And the idea that occurs to most people is Venus is closer to the sun. And here's a picture. Kim mentioned my exhibit on the National Mall. So this is, if you go out there, this is the Air and Space Museum right along there. And that's the sun at 1/10 billionth of actual size right there. And then there's the pedestals for Mercury, Venus, Earth. So on this scale, Earth is smaller than the ballpoint in your pen compared to that grapefruit size sun. And what you see is, sure enough, Venus is closer to the sun than Earth. However, if you think about it, and a good way to think about it is imagine that there's a giant bonfire here where the sun is. And then you walk to Venus and you walk to Earth and you feel the heat. Well, yes, you will feel more heat over here at Venus, but you can kind of tell just by thinking about walking from the bonfire, it's not going to be enough of a difference to explain that. That's way too big of a difference to be explained just from the distance to the sun. In fact, it turns out it's even more interesting than that, because you'll notice that Earth has clouds, some, right? You can also see through to the ground, and clouds reflect sunlight. Venus, the entire planet is covered with clouds, and they reflect a lot of sunlight. So it turns out that Venus, even though it's closer to the sun, there's actually less sunlight reaching the ground because the clouds reflect so much of it away. So if the temperature was about sunlight, Venus should be colder than Earth, but it's not. It's really hot. So how do we explain that? Well, scientifically, we now know the answer, which is something called the greenhouse effect. And that is that energy from the sun comes in, and some of it's reflected back to space, and that's why we can see the ground. The reflected sunlight is what our eyes see. But some of it is absorbed by the ground, heats the ground up, and that energy gets returned in the form of infrared light, which is what these red arrows represent. But the thing about infrared light is that there are certain molecules that are very good at absorbing it. Most of our atmosphere is made of nitrogen and oxygen, which don't absorb it at all. But there are a few molecules in our atmosphere, in particular carbon dioxide, water vapor, and methane, that do absorb infrared light. And so the blue represents those greenhouse molecules. So when the infrared light goes up and hits one of those, it gets absorbed and then it gets re-emitted in some random direction. So you can see that the result is the more of these greenhouse gas molecules you have, the longer it takes for this infrared light, the heat, to escape back to space. So the way to think about this is it's exactly the way a blanket works. So if you go outside on a cold night, and you're cold, and you wrap a blanket around you, you get warmer. Why? The blanket isn't hot. It's not giving you any heat. What the blanket is doing is it's holding your own body heat in, and that's what makes you get warmer. And that's exactly what greenhouse gas molecules do. They hold Earth's own heat in, or a planet's own heat in. And that's why greenhouse gas molecules, more greenhouse gases, make planets warmer than they would be otherwise. So now if you're thinking about this scientifically, the next thing you should be saying is, well, that sounds like it makes a lot of sense, but how do you know it's true? And the way we know it's true is two basic ways. Well, really one way, but validated by a second. And the way we know it's true is we can actually measure this directly in the laboratory. I'm telling you that gases like carbon dioxide absorb infrared light. Well, that means in principle you can put carbon dioxide in a tube and shine infrared light on it and measure what happens, right? That was done starting in 1859. That's the experimental apparatus from 158 years ago when it was first measured. So we have understood this greenhouse effect and in fact measured it quantitatively for more than 150 years. This is not a new idea in science. The greenhouse effect's well understood, very well measured, and based on that you can see exactly how it's going to affect the temperature of planets. And the only question is, sometimes what you measure in the laboratory might work differently in the real world because there's other complications of the real world that you don't have in the laboratory. So what you do is you say, okay, we need to test this in the real world. How are we going to do that? Well, we have real worlds. We have the Earth, we have Venus, we have all the other planets and moons in our solar system. So what you do is, based on those measurements that you made, you calculate, if we're correct about the greenhouse effect, and you've measured how much greenhouse gas each planet, each moon has in its atmosphere, then the temperature should be this. And then you say, if we're not correct, and there is no greenhouse effect, what would the temperature be? And guess what? You get the right answers when you use the greenhouse effect, and you do not get the right answers when you don't use it. So that validates that what we're measuring in the laboratory is in fact real. Based on the amount of greenhouse gas in the atmosphere of Earth or Venus or any other planet or moon in the solar system, you can calculate the expected temperature from what we've measured with the greenhouse effect in the lab, and it turns out that is the actual temperature. So there's no doubt at all that this is correct, that the greenhouse effect is what warms planets compared to what they would be without it. So what's going on? Well, on Earth, you see here it says enough carbon dioxide to make our planet livable. We have a naturally occurring greenhouse effect on Earth. And it turns out that's really important, because if you calculate what Earth's temperature would be if there was no greenhouse effect, if there was no carbon dioxide in the atmosphere, it turns out at our distance from the sun, it would be too cold to have liquid water on this world. The oceans would be frozen, or there would be no oceans. So the only reason that we're alive is because there's a naturally occurring greenhouse effect that makes this planet warm enough for life. It's a pretty significant effect. Without it, the temperature would be 30 degrees Celsius, or about 60 degrees Fahrenheit cooler than it is. That greenhouse effect is causing a lot of warming on Earth, and that's why this planet is livable. But now, you say, well, what's going on with Venus? Venus has 200,000 times as much carbon dioxide in its atmosphere as Earth does. And when you calculate the expected temperature for Venus with so much carbon dioxide in the atmosphere, guess what the calculations give you? The actual temperature of Venus. So basically, we're almost kind of done with the science, but I'm going to keep going anyway. But you see, we know the greenhouse effect is real. We know that the more of this gas you have, the warmer it's going to be. And as soon as you know that, you might think, okay, well, that could be a problem if we were causing more greenhouse gases to go into the atmosphere. And that was identified as a potential problem by a famous Swedish chemist in 1895. That was when global warming first came to attention. However, at that time, we were adding so little carbon dioxide to the atmosphere that he did a calculation and found that at the amount we were emitting, it wouldn't be a problem for hundreds of years. What he didn't predict was the invention of the automobile. And so now, starting, as people thought more about this and said, well, we should have some data, starting in the late 1950s, scientists from Scripps Institute at UCSD, in particular Roger Revelle, for whom Revelle College is named, and his student Charles David Keeling, this graph is now called the Keeling curve after him, started measuring the carbon dioxide concentration in Earth's atmosphere. And the units here are called parts per million, so it's out of every 1 million molecules of air, how many of them are carbon dioxide? So back in the late 50s when he started, about 315 out of every 1 million molecules of air was carbon dioxide. It's a very small concentration, right? 1% would be 10,000 parts per million. So this is way less than 1%, but it's really important because it's the part that absorbs the infrared light. And what he noticed within just a few years, and he was not expecting to find this, he was very surprised, was that it was clearly going up at a fairly rapid rate. And you can see from the late 1950s, 315 parts per million, it's up over 400 parts per million today. That's a tremendous rate of increase. And so if you already know that an increase in carbon dioxide, more greenhouse gas, makes planets warmer, you look at this and you go, that could be a problem. So then you say, well, what might not make it a problem? What might not make it a problem is if this is just natural and not us. But guess what? You can measure that. Because when you burn fossil fuels, they release carbon in different isotope ratios than carbon coming from other sources, natural sources like volcanoes and so on. And guess what? The isotopic composition of this carbon dioxide matches that of fossil fuels. There's zero doubt that this is our carbon dioxide going into the atmosphere. The other question is, could it be that, well, even if this is our carbon dioxide, maybe the carbon dioxide concentration varies naturally anyway, so then it wouldn't be a big deal, because that's only 50, 60 years worth of data. what about before this? And so what you'd really like to know is, what was the carbon dioxide concentration like before that? And you might think that would be very difficult to figure out because nobody was measuring it. However, it turns out there's a bunch of ways to figure out what the carbon dioxide concentration was before that. And the very best way, where you get the cleanest data, is by drilling into the ice, like in Antarctica, and bringing up these tubes of ice. And when you look at these tubes, well, what is ice in Antarctica? What it is it's the snow falls, and then it doesn't melt. And the next year, more snow falls, and then it doesn't melt. And the next year, more. So it piles up year after year. And actually, when you look in one of these ice cores in detail, you can actually see the layers, kind of like counting tree rings. You can count back through these layers and say, oh, there's 10 years ago, there's 20 years ago, there's 30 years ago, and so on. And some of those layers have bubbles of air trapped in them. So basically, you have to be very careful about it. You just grab one of those bubbles of air and measure its carbon dioxide concentration. And then you know what it was whenever that snow fell. The deepest ice core that's ever been drilled, done a few years ago down in Antarctica, they drilled down 2 miles into the ice. They have a continuous ice core, basically, that they brought up 2 miles long. They cut it into sections this size to store in the freezers to make the measurements. But we have a 2-mile long ice core, and at the bottom of that ice core, when you count back the layers, you are looking at snow that fell 800,000 years ago. So we have an 800,000 year record of the carbon dioxide concentration, and there it is. This is 0 is today. This is going back in hundreds of thousands of years to 800,000 years ago. And what do you see? This is the carbon dioxide concentration. What do you see? Yeah, it does vary naturally by quite a lot. However, it varies naturally. It's been between about 180 parts per million and 280 parts per million. In fact, in 1750, which we put at about the beginning of the Industrial Revolution, it was 280 parts per million. But since 1750, it has shot up, as we see expanded here, to over 400 parts per million. In other words, where we are today is 40% higher than it has been any other time in the past 800,000 years. Moreover, if you say, what happens if we do nothing? There was also some news today about somebody doing nothing. If we continue, if that continues upward at its current rate, what happens? By 50 to 60 years from now, we will not be at 400 anymore, we'll be at 560 at the current rate we're going. In just 50 to 60 years from now, 560 will be double what it was at the start of the Industrial Revolution. And as I told the high school kids today, 50 or 60 years from now means they're barely going to be older than I am now. And you'll have that concentration having gone from 400 to 560. And by the middle of the next century, it would be triple that value, something that the Earth hasn't seen in many, many millions of years. So this is clearly very different, and it brings, I have to look down to make sure I know what slide's coming next. You know, I should move it so I can see it better. We're kind of done with the science, but I want to summarize it, and this is what I call global warming 1, 2, 3, because this is the part that they never tell you about on the news. That's really, really simple. Number 1, it's a fact that carbon dioxide makes planets warmer than they would be otherwise. I've shown you how we know that. It's not something that anyone disputes, at least anyone with any science training. No one disputes this fact. And I showed you the measurements that prove that the carbon dioxide concentration is rising. And if you think about it, if this gas makes planets warmer and we're adding more of it, it's pretty obvious what's going to happen. It's going to get warmer. And if you listen carefully, even to what the debate you might hear in the media is, you will never ever hear anyone, at least with any scientific training, dispute this. There is zero doubt about this. So you say, well, how is it that I hear scientists come on TV and say they don't think this is a big problem? It's because if this says global warming is going to happen, it does not tell you how fast it's going to happen or how bad it's going to be. So there is room for debate about how fast it's going to happen and how bad it's going to be. But there's zero debate about the fact that it is going to happen. And like I said, that's the big picture that gets missed in the news most of the time. And this is where I come to my quiz question, which is that this is so simple and clear and easy to understand, like we've just talked about it, that you would think that even politicians could understand it. And so the quiz question is, who was the first major global leader to say, this is a real problem caused by us that we must do something about? Okay, so I have to clarify my question a little bit. Al Gore probably was ahead of anyone else in recognizing this. However, in 1989, outside of Tennessee, nobody had heard of Al Gore. The person that they'd heard of in 1989, who gave a major speech to the United Nations, she said this: "What we are doing to the world by adding greenhouse gases to the air at an unprecedented rate is new in the experience of the Earth. It is mankind and his activities which are changing the environment of our planet in damaging and dangerous ways." Margaret Thatcher. So if anybody ever tries to tell you that this is a political issue, conservative versus liberal, Democrat versus Republican, all you have to do is tell them, hey, the first person who said this is a major real issue that we need to do something about was one of the two founding icons of modern conservatism. Pretty clear it wasn't political in 1989, which means it's not political today either, unless people try to pretend that it is. Because I want to make sure we have some time for discussion, I'm going to go a little more quickly than I normally would through the kind of debate that you hear in the news. And so I'll just show you a couple things. But again, I have a whole chapter in the book that you can read for free online, remember, that goes through all the general skeptic questions that you hear raised in the news. And a lot of them are at least possibly valid, right? We don't know for sure how fast it's going to happen or how bad it's going to be. And the question is, how concerned are you about it? And this is where what you've heard of as the scientific consensus comes in. It's not a scientific consensus to have the 1, 2, 3 science. That's just 100% fact. The consensus is that 90+% of climate scientists think it's going to be fast enough and bad enough that we better do something about it now. There's a few percent who think maybe there's factors in the climate that will keep it slow enough and not bad enough that we don't have to deal with it immediately. So I'll show you some of the reasons why I think it is in that bad part. So the first is, this is a graph of the global average temperature for the past 130 plus years. 1880 is about as far back as measurements go, because in order to measure the global average temperature, you need temperature measurements from all around the world. And people weren't collecting them before that. And there's bigger uncertainties as you go further back because there were fewer measurements. Today we have very solid data. But the zero line is the 20th century average temperature, and what you see is a very clear trend. It is getting warmer. Why? Because the 1, 2, 3 science is true. It really does make planets warmer. And if you look at this rate, that does not look like a slow rate of change. It looks to me like something we should be very concerned about. I'm going to skip ahead to here. Another question that comes up is, well, the climate varies naturally. Why should we be concerned about this climate change when the climate varies naturally anyway? So here you have the same data that I showed you before from the 800,000-year ice core record of the carbon dioxide concentration. It turns out from those gases in the trapped air bubbles, it's a little harder because it's not a direct measurement. But you can also use those gas bubbles and other gases in there to infer what the temperature was on Earth at different times in the past. So the yellow curve up here is the temperature record. And you will notice these are degrees Celsius, so if you're thinking in Fahrenheit, like most Americans do, double those numbers. So these are huge changes in temperature up and down. What's going on? Every one of these down parts is what we call an ice age, right? Every one of the up parts is what we call a warmer interglacial period. You know, there was the most recent ice age here, and we were in the interglacial period already when human civilization arose. And what do you notice? Well, you notice a couple things. First of all, the temperature is high when the carbon dioxide concentration is high, and the temperature is low when the carbon dioxide concentration is low. Why? Because you're seeing the 1, 2, 3 science again. Carbon dioxide drives the temperature. Incidentally, we could talk about it later if you want, but you might be wondering what's driving these natural things. It turns out it's very small changes in Earth's rotation and orbit that cause these small changes that affect the carbon dioxide concentration and temperature a little bit, and then it's an amplification process once it gets going because the two things feed off each other. But the important point is they do go hand in hand, and the other thing is you see these changes in natural carbon dioxide, they were only between 180 and 280 parts per million, but look at the gigantic swings in temperature, 10, 12, 14 degrees Fahrenheit that they caused. We're now dealing with a much larger increase in the carbon dioxide concentration, which might make you worried that we could be seeing a very large increase in the temperature here. Now, fortunately, when people do computer models, there are some mitigating factors in the natural climate that make people think that it won't get as bad as that graph might make it imply. But you probably hear in the media sometimes people who are saying global warming is not a big deal say, well, because you can't trust the models. Well, I think you can trust the models. But if you can't trust the models, the alternative is to trust the data, and the data say it's going to be even worse than the models do. And so now we'll turn and go to the consequences of global warming. If you want to think about whether this is a real problem, you have to think about what else is going to happen. We've talked about the fact that it's getting warmer, but what does it mean to get warmer? Why should we care? You know, if you live in the Northeast, you might think, hey, warmer sounds nice, winter won't be so bad, right? Why should you care? Well, for one thing, it's an average warming. Regionally, the reason a lot of scientists prefer to call it climate change than global warming is that temperatures in different places will warm by different amounts. So this is a map made by NASA that shows that same kind of temperature data I showed you before as the graph, but instead of showing an average for the whole world, it shows you the different places around the world and what their temperatures were. And so this shows you temperatures around the world between the years 1880 to 1884. So it's a 5-year moving average if you're looking for the technical details on it. And blue is cooler, red is warmer. And so this is a little video that NASA made that shows what has happened to the temperature on Earth since 1880. And so I'll start it running, and you can see things get warmer, things get cooler, and as you go through the first few decades, there's no obvious pattern. But keep watching. Now there's an obvious pattern. What else do you notice about this pattern? You notice different regions of the world warm more than others. The Arctic is warming the most, which is why you hear so much about decline of sea ice and so on, which I'll talk about again in just a moment. This regional climate change has not only effects on different places warming more or less than others, it also has effects on other things like rain, drought, and so on. And it's not 100% one-to-one correlation, but in general, the trend is places that were dry before tend to get even drier. And places that were wet before tend to get even wetter. So what do you see? In places like Southern California, Colorado, where I'm from, things have gotten drier. More drought, more wildfires, and so on. In places that have been wet before, there's more flooding going on around the world, and so on. So we see these effects of regional climate change that have real major effects. They have lots of other effects. For example, things like the Zika virus, right? The mosquito-borne virus. In the past, that would not have come up to the United States because the temperatures weren't warm enough in the US. But with climate change, these diseases are migrating further north than they used to. So a lot of what we see with things like the Zika epidemic, you can trace back to, at least in part, being maybe not caused by global warming, but being made worse by global warming. Weather, in general, is what is weather? Weather is driven by energy in the atmosphere, right? Energy that comes from the oceans and from the winds and so on. Weather is energy. When you trap more heat, as our blanket does with our global warming 1, 2, 3, that means there's more energy, which means there's more energy available to drive weather, which means you're going to get more extreme weather. And that's exactly what we're seeing around the world, more extreme weather events than there used to be. The melting of sea ice, like I mentioned before, is comparison of the Arctic sea ice in the summer in 1980 to 2012. There's a graph showing you the decline. It isn't always the same from year to year because climate's complex, but it's very clear the amount of summer sea ice is going down substantially. And that's very concerning on a number of levels, one of the most important being that ice reflects a lot of sunlight. Water absorbs sunlight. So when you have less summer sea ice, that means more sunlight gets absorbed, which means it's going to amplify all the other effects of global warming that would be happening anyway. So you get an amplification process of everything else. Sea level rise. Sea level rises for a couple of reasons. The simple, well understood one is that seawater actually expands a bit as the temperature gets higher. It's a very, very tiny amount of expansion. You'd never be able to measure it in a cup, but in 2 miles or a couple miles deep of ocean water, you can notice that. And sea level has already risen over the past century or so by about a foot. And that's been tied, for example, to the greater storm surge that you see in things like Hurricane Sandy and so on, because that 1 foot rise in sea level when a storm surge comes in is going to be magnified. And thermal expansion will raise sea level. There's really nothing we can do about this. It's going to raise sea level by about another foot by the end of this century. The bigger concern is that there's another contribution to sea level rise, which is ice melting into the oceans. And that's ice from glaciers, particularly Greenland and Antarctica. The problem there is scientists do not understand ice melting very well at all. I mean, obviously we know what causes ice to melt, but in terms of how quickly the ice from Greenland or Antarctica can melt and flow into the ocean, nobody has a really good understanding of it. And so there's a huge range of estimates. The generally most common estimate of what will happen is that by the end of this century, ice melt will cause sea level to rise by about 1 meter, 3 feet. So think about that down in Mission Beach or Pacific Beach, Ocean Beach, what a 3 foot rise in sea level is. That's what most people think is the most likely thing to happen. However, there has been some work done that suggests it will be a much more significant rise than that. Some of the models have said that it could be a 6 meter rise in sea level. That's 20 feet by the end of this century. And then a couple weeks ago, some people published some work saying, wait, it's happening faster than we thought. It could be that by 2050. That's 33 years from now. The high school kids here and the younger kids, they won't even be as old as some of us at that point. Imagine 2050, sea level being 20 feet higher than it is today. What would that do to San Diego? Okay. Now that's unlikely. Very few scientists think it'll be that bad, but we can't rule it out. And it's a possibility that it can happen that quickly. And then the longer term is what would happen if all the ice in Greenland or Antarctica melted. Now this would, even in the worst case scenarios, this would probably take at least 1,000 years to happen. So in principle, you could adapt to it by moving inland, right? But it has this really interesting thing that basically if we melt all the ice in Greenland and Antarctica, sea level will go up by 240 feet. That would mean 1,000 years from now, your descendants will need deep sea diving equipment to visit the homes you used to live in. Kind of an interesting way to think about this issue. And the last consequence I want to talk about is called ocean acidification. Carbon dioxide isn't only released into the atmosphere, it's also dissolved into the oceans, and there it turns the ocean water more acidic, and that's been implicated in declining fisheries, coral bleaching, and various other things. So these are the kind of consequences that we're concerned about with global warming. Again, we can't tell you for sure how fast any of these will happen or how bad they're going to be. And some people will argue that they're not going to be that bad. But what risk are you willing to take is the question. And part of the answer to that depends on, if you want to do something about it, how much is it going to cost you, right? How much risk do you have to take to do something about it? And this is where I think the subject gets really interesting, because this is, into my opinion, we're at the last part of my talk, a very solvable problem. And the reason it's a solvable problem is because it's a really easy problem in principle, not there's practical difficulties, right? But the principle is really simple. We know what's causing it, burning fossil fuels. Therefore, solving it is really easy. Stop burning fossil fuels. Okay. But then you got the question of, well, we like having lights and air conditioning and all that stuff. So if we're not going to burn fossil fuels, where are we going to get energy from? Well, it turns out we got plenty of other ways that we can get energy from already. 3 in particular. Efficiency. And you don't often think of efficiency as an energy technology, but it is. If you only need half as much energy to cool your home or light your lights, then that's that much less energy that you need to get somewhere. Renewables. Wind and solar, in particular. For example, solar power, the amount of sunlight hitting Earth every day is 20,000 times what we as a species use in energy. So if we could just tap 1/20,000th of the solar energy coming into Earth every day, we could have all of our energy being supplied with that, with no change in our living standard, because we'd have just as much energy as we have now. Now there's some practical difficulties in doing that. You need to have that many solar panels, you need to have a way to get the electricity through the grid, you need to have battery storage so that at nighttime you can store the energy, and some of those problems haven't been solved, but it's very clear that there is plenty of potential for renewables. And the third technology is nuclear, which different people have different opinions about whether nuclear power is safe and a good idea, but it does not emit any greenhouse gases. So in terms of global warming, nuclear is one potential solution. My personal opinion is that we can do nuclear with new technologies much safer and with less waste than we have today, so I would include that in the solution. But it doesn't really matter one way or the other. The point is, we have the technology already to solve this problem. And there's future technologies that are even more incredible. For example, on the solar, if you don't want to have the battery storage and worry about the nighttime in clouds, put your solar panels in space and beam the energy down to Earth. It's kind of a cool idea that some people are working on. Nuclear fusion, algae-based biofuels. Craig Venter up at the Venter Institute up by UCSD is working on that. There's all kinds of technologies in the future that might do even better. But we already have the technology that we need. And so then the question is, why aren't we switching if we have alternatives already available? And the usual answer that's given is because these alternatives cost more. But what if they don't? What if it's an illusion that these alternatives cost more than fossil fuels? How could it be illusion? It could be an illusion if you're paying for fossil fuels in ways that you don't realize you're paying for it. So this is what I call the socialized costs of fossil fuels. And I'm not talking about fake money or imaginary economist money. I'm talking about real money. I'm talking about money that you are actually paying. It's just that you don't pay it when you go to the pump to buy your gasoline. You pay it a different way. For example, the National Institute of Health says that we spend $120 billion a year as a nation on air and water pollution related hospitalizations. Asthma attacks, all these other kinds of things. That's not fake money, that's money that is actually being spent, that $120 billion a year. You're paying for it through your insurance premiums and your tax dollars. You're just not paying for it at the time you buy the fuel. The Department of Defense says we spend at least $100 billion a year protecting the global oil supply. That's real money coming out of your taxes. That if we didn't have a global oil supply that we needed to protect, we wouldn't have to be spending. There's direct subsidies and tax write-offs for fossil fuel exploration and so on. And the really amazing thing is if you just take these three things, which nobody disputes, right? These are real costs, real dollars coming out of your pocket, and divide them by the amount of gasoline we use, that's a subsidy of $2 per gallon. So what you're paying for gas is actually $2 per gallon less than you're actually paying for the gas. It's just the rest of it's coming out from your taxes and your insurance premiums instead of at the time you buy the gas. What if gas costs $2 more? Well, then it wouldn't be cheaper than the alternatives anymore. And that's only the beginning. Think about how much we spend on protecting ourselves against terrorism as a country today. Right? What is the impact of terrorism on our economy? It's huge, right? Where do terrorists get their money from? And by terrorists, I'm talking about ISIS, Iran, Russia, pretty much any bad country you can think of. Where are they getting their money from? Oil. If we weren't buying it, they wouldn't have money to fund their operations. So there's actually probably a lot more direct cost to us than just what is easily quantifiable ones. And there's a bunch of more. In fact, the IMF did a study in 2015 and concluded that global subsidies for fossil fuels are $4 trillion per year. If instead of subsidizing them with these other dollars, that was built into the cost, no one would buy these things. Everybody would be buying solar, wind, nuclear, efficiency, investing in these future technologies, and so on. The problem is we have a false economy for energy. So then you can ask, well, how do you get a clear economy? How do you make the market work correctly for energy? The way you do that is you build all those socialized costs into the price. And this is what's called the conservative answer to climate change, because this was a proposal that came out recently. It's been proposed by others before too, but recently from this group of high-level advisors to the last 3 Republican administrations. This was their plan. They call it a carbon tax and dividend. So what they do is they apply a carbon tax. So when you buy fossil fuels, you pay a carbon tax. You pay a tax that incorporates these other costs. Then the market gives you an incentive to buy other stuff, right? The only difficulty is they're conservatives, they're Republicans. They don't want the government to have more money. And a tax collects money, right? So what they do is they say when the government collects the carbon tax, it basically goes into a special bank account. And then every month, the government takes every single dollar that's in that bank account, minus the administrative fees, and sends it back to you in the form of a dividend check to every family in the United States. Thereby, the government has no extra money because it's giving all the money it's collecting back, but because it's giving it back in equal amounts to every family, that means those who use less have a greater benefit. So you're strongly incentivized to use less fossil fuels. And they say that this strategy will strengthen our economy. Now, let's go through their argument here. How does this strengthen our economy? Because remember, the real cost of fossil fuels is higher than all the alternatives. So we're actually today using something to get energy that costs more than we should be paying. If we switch over like this, we'll be paying less for the same amount of energy. That helps our economy, because we're paying less for the same thing. Reduces regulation, right? They're Republicans, they don't like regulation. But why do we have regulations relating to the climate, like what Obama put in place? Because you're trying to get people not to use too much fossil fuels. If you have a carbon tax, they'll stop using them without regulation, just because the price is right. So you don't need all the regulations anymore. Help working class Americans. Why? Because those dividend checks coming back every month. If you manage to not use a lot of fossil fuels, you'll be actually getting a check that will help you out. Shrink government and promote national security. Well, it shrinks government because you don't have all that regulation anymore, and it promotes national security because you're not giving money to terrorists anymore. So you think about that, and on top of that, you're getting rid of air and water pollution, because that's all caused by fossil fuels too. And it brings me to my favorite cartoon, which is the guy up here speaking about all the things that happen if we switch our economy away from fossil fuels. And then you have the person in the audience saying, but what if it's a big hoax and we create a better world for nothing? And what you see here, this is part of why I think this is a politically solvable problem. Because even if you still don't believe in the science after all I've told you, it still makes sense. Economically, security-wise, and in every other way. So to leave you, I want to give you a couple of thoughts on how I like to personalize this issue. How do you get people to get this into their heads and really think about it? And the way I like to do it is by thinking about the fact that on average there's about 25 years between generations, right? You are 25 years younger than your parents and 50 years younger than your grandparents and the other way around. So what that means is that it means no matter how old you are, on average, in 50 years, if you have grandchildren, they will be your current age 50 years from now. So if you're my age, pushing 60, I will have, on average, grandkids pushing 60, 50 years from now. If you're in high school right now, on average, you'll have grandkids who are high school students 50 years from now. So what I want you to do is think about writing a letter to your grandkids, and you're going to seal it in a time capsule for 50 years. And this is what you write, right? To be opened in 50 years. Dear grandchildren, as I write this in 2017, many people are arguing about whether global warming is a real problem, and if so, how serious it will be for you when you were my age. I have examined the evidence, and I have decided to, and then you fill in what you're planning to do. Hope your world is a good one. Love you. What are they going to think when they open that letter 50 years from now about what you decided to do? And so I'm going to leave you with two more quotes. First one here from Ronald Reagan. What is a conservative after all but one who conserves, one who is committed to protecting and holding close the things by which we live? This is our patrimony. This is what we leave to our children. And our great moral responsibility is to leave it to them either as we found it or better than we found it. So that's basically Reagan's version of the letter to your grandchildren. And the last quote I'm going to leave you with, I have to tell you first off about the context. This quote is from Speaker of the House Paul Ryan, and he was not talking about global warming when he said this. He was actually talking about his decision to accept the nomination to be the Speaker of the House. However, the quote is so perfect that I am optimistic that someday he will think through these issues and apply exactly the same quote to global warming. And this is what he said. My greatest worry is the consequence of not stepping up, of someday having my own kids ask me, when the stakes were so high, why didn't you do all you could do? Why didn't you stand up and fight for my future? And I think if we can get everybody in Congress and in politics to think about this. Oh, and I probably should have mentioned this earlier, but another way to realize the non-political aspect of this is that in this country today, we have a very, very polarized political environment, right? People disagree about almost everything. But I have one thing that I'll guarantee you that nobody disagrees about. Whether you're the extreme right wing or the extreme left wing or any place in between, everyone agrees that we want a better world for our kids and grandkids. You won't find anybody who says, no, I don't want them to have a better world, right? Everybody wants a better world for their kids and grandkids. And therefore, when we think about it in these ways, I think we can come to agreement. And personally, I like the carbon tax and dividend idea that came from those Republican officials. You might have other ideas about how you want to deal with it, but I think we can come to agreement. And so just to close out here, I want to tell you about a couple other little things. That's the book that I've been talking about from globalwarmingprimer.com. I also have a children's book on this topic called The Wizard Who Saved the World, and there you can see it being read from the International Space Station. And you can watch the video of it being read from the International Space Station at Storytime from space.com. In fact, all 6 of my kids' books are up there on the space station, have been read by the astronauts. And that was kind of a really cool thing. I was excited when they called me up and said they wanted to do that. And then the other thing is this total eclipse coming up this summer on August 21st. I won't spend much time on it, but San Diego, there will be about a 50% partial eclipse here. That's cool. Don't be here. Be on that blue path where you'll see 100% total eclipse. During the 100% total eclipse, the moon will completely cover the sun. You'll see these streamers of the sun's corona off there. You'll be able to take your eclipse glasses off for those couple minutes. You'll see stars and planets in the daytime sky because it will become dark. It's an amazing amazing experience. So I'll just show you briefly, I have an app that I've created, Totality. It is free. So download it. If you go to the iOS store, just search on Totality by Big Kid Science, and you'll get it now. If you have an Android phone, wait a couple weeks because it's not available yet. But it should be, hopefully the Android version will be done in about 2 weeks or so. And I have a quick little video that tells you how the app works.
Are you ready for the Great American Eclipse of 2017? Totality by Big Kid Science is the app that you'll need. Explore and search the map, or select My Location to find out when and what you'll see on Eclipse Day. Or select Nearest Totality to find the closest location to observe a total eclipse. Cool navigation tools will help you find your best route to the path. And our resources section will help you learn about safe viewing, how eclipses work, activities, and much more. Totality by Big Kid Science, getting you on the right path to Eclipse Day.
And so Kim's got the glasses there. I hope you will buy some to support the Alumni Association, and they also have the name of the app on them. And those are my children's books, the ones that are all up on the space station. This is what we're talking about tonight. Some of my other books there, and we can go to questions. Thank you.